Okay, in this video we're going to look at a solution to problem A2 from the 2016 Putnam Exam. So the statement of the problem is as follows. So given n a natural number, in other words a positive integer, let's let m of n be the largest natural number m such that this binomial coefficient m choose n minus 1 is bigger than the binomial coefficient m minus 1 choose n. And then our goal, after kind of getting an idea for what this largest capital M of n is to evaluate the limit as n goes to infinity of m of n over n. And then let's just recall that the binomial coefficient is defined in the following way. So if you have two natural numbers r and k, r choose k will be r factorial over k factorial r minus k factorial. And actually there's a more general definition for kind of an arbitrary complex number in this upper entry, but this is the definition or the equivalent formulation that we'll need in this setting of natural numbers. Okay, so let's look at the solution. So notice that this inequality right here, which I will call inequality star, is the same thing as the following. So if I divide both sides by the right-hand side, we can see that inequality star is the same thing as saying m choose n minus 1 divided by m minus 1 choose n is bigger than 1. And obviously we can only do this division if this part is bigger than 0, but our setup kind of guarantees that. Okay, good. And now from here we can use this equivalent formulation of the binomial coefficients to break up each of these parts. So notice that this is equivalent to m factorial over n minus 1 factorial, and then we have m minus the quantity n minus 1, which is the same thing as m minus n plus 1 factorial, over, now we have m minus 1 factorial over n factorial, and then m minus n minus 1 factorial. In fact, it's like m minus 1 minus n, but I've put it in a different order there. So now that's going to be the same thing as saying that this is bigger than 1. Now what I want to do is take this big complex fraction and write it with like numerators and like denominators. And what I mean by that is I want to think of m factorial and m minus 1 factorial as being kind of like terms because I can do some simplification with those. So I can take this big fraction and rewrite it as m factorial over m minus 1 factorial times n factorial over n minus 1 factorial. So notice this is in the numerator of the numerator, and this guy is in the numerator of the denominator. But now n factorial is in the denominator of the denominator, so that flips up to the numerator, and n minus 1 factorial is in the denominator of the numerator, so that stays down here. Okay, good. And then we also have m minus n minus 1 factorial over m minus n plus 1 factorial. And so that's equivalent to this guy being bigger than 1. But now we can do a lot of simplification here. Like, for example, we'll use all three of these. So m factorial is equal to m times m minus 1 factorial. And then similarly, n factorial is equal to n times n minus 1 factorial. Good. And now notice this guy in the denominator here is 2 more than this guy in the numerator. So that means we can write m minus n plus 1 factorial as m minus n plus 1 times m minus n times m minus n minus 1 factorial. Okay, great. But now that allows us to do lots of simplification here. So notice this guy is going to simplify to m, this guy is going to simplify to n, and then this guy is going to simplify to something in the denominator. And what we're going to get in the denominator is m minus n plus 1 times m minus n. And so just to reiterate, what we have here is our inequality star, which is the inequality that we're really interested in, is equivalent now to this inequality. So we have m times n over m minus n plus 1 times m minus n. But now we can do one more thing. Let's cross multiply to clear the fractions here. And notice that that's the same thing as m times n is bigger than m minus n plus 1 times m minus n. Great. But that is the same thing as m minus n plus 1 times m minus n minus m times n is less than 0. And you might say, well, why do we want to do that? Because now we can view m as a quadratic polynomial in variable n. Okay, great. So I'm going to bring this to the top, and then we'll move on to the next step. Okay, so on our last board, we argued that this inequality star was equivalent to this nicer inequality. So now what I'm going to do is I'm going to multiply out these two terms, and I'll have a quadratic polynomial in m. So notice this is going to be the same thing as m squared, and then we're also going to have minus 2mn. So let's see where we get those. We have m times minus n and minus n times m. Okay, good. And then plus m. We get that from m times 1. And then finally, we also have plus n squared minus n. So there we have n times n, and both of those are negative, so we get n squared, and then minus n from that, and then minus mn is less than 0. So now it's equivalent to that. Okay, so now I want to view this as a quadratic polynomial in m. So notice I have m squared, so that's going to be by itself. And then these things that I'm underlying in red are all of my terms, which will give me something with a coefficient of m. So I can write this in the following way. So this is going to be plus minus 3n plus 1 times m. So notice here we have minus 2, minus 1, so that's going to give us minus 3n. Great. And then now we have plus n squared minus n is less than 0. And also notice that if we think of this as an upward facing parabola in the n and m plane, so it would look something like this. So don't pay no mind where I'm putting it in the plane, but notice that the values where it is less than 0 are going to be between the two roots of this equation. Maybe we could call this root right here ln, and this root right here un for the lower root and the upper root. So it might be important, and it is important, to find out where this equation is equal to 0. Because in between those two places where this is equal to 0, we know that our inequality is satisfied. So let's go ahead and find the n values that make this equal to 0. And we can do that with the quadratic formula. So we can have m equals, so it'll be negative b, so that'll be 3n minus 1, plus or minus the square root of, so we have b squared. So notice that's going to be minus 3n plus 1 squared minus 4 times a times c. Notice the coefficient here is 1, so we just have 4 and then n squared minus n. And this is going to be all over 2. Okay, great. So now notice that's going to give us the following thing. So we have 3n minus 1 plus or minus. So let's see, we're going to have 9n squared minus 4n squared. So that's going to give us 5n squared. Good. And now notice my cross term here is going to be 6n, so, and it's going to be negative, and then my term here is going to be plus 4n, so that's going to give me minus 2n, and then plus 1, because that's going to be my only constant. Great, and then now this is all over 2. And now what I can do is I can take ln to be equal to the lower root. So in other words, the lower root is 3n minus 1 minus the square root of 5n squared plus 2n plus 1 over 2. And then I can let un be the upper root. So here we have un is equal to 3n minus 1 plus the square root of, and I won't write that in there because I don't have enough room, but it's the same thing as what we have up here, 5n squared minus 2n plus 1. So if we have n between these two values, we know that this inequality is satisfied. All right, so I'll clean up the board and we'll pick up from that point. Okay, so on the last board, we worked out this defining inequality for m to the following. So we have, it is equivalent to n lies between this L of n and this U of n, where L of n is defined to be this. Recall that that was the smaller root of a polynomial, and U of n was that which was the larger root of a quadratic polynomial. So now we have really two important questions here. First of all, are these definitely real numbers? So if these are not real numbers, if they're complex numbers, then we have a problem. So let's just first check if these are real numbers in the first place, and we can do that by looking at what's under the square root and showing that what's under the square root is always positive. And the way we can do that is by looking for roots of 5n squared minus 2n plus 1. So in other words, we're going to show that 5n squared minus 2n plus 1 is always bigger than 0. And we'll do that by solving the equation 5n squared minus 2n plus 1 equals 0. And notice we'll use the quadratic formula for this. So that's going to give us n equals, so that's negative b, so we'll have 2 plus or minus b squared, which is 4, minus 4 times a times c, so minus 4 times 20, so we have that, over 2. So we get something like that, but now notice that this is equal to 1 plus or minus, this is the square root of negative 16, so that's going to be 2i. Well, it'll be 4i over 2, but then that'll be 2i. Okay, great. So what that tells us is that this is not equal to 0 for all n in n. Right? Because the only n that makes it equal to 0 are complex numbers. So this is not equal to 0 for all n in n, but what that tells us is that it is either always positive or always negative. But we can see that the choice is that it will be always positive, because if we plug in, for example, n equals 1, we'll see that we get a positive number here. So this thing is always positive. Great. Now the next thing that we need to show is that there is an n between L of n and U of n. And how we can do that is showing that U of n minus L of n is bigger than 1. Right? So if it's bigger than 1, that means there's definitely a natural number between them. If it's less than 1, then there may not be a natural number between these two. And so how can we do that? Well, we'll just do the difference of these two. So notice if we do the difference of these two, what will we get? So we'll get the 3n minus 1s will cancel, and we'll just get the square root part. So notice we'll get the square root of 5n squared minus 2n plus 1 has to be bigger than 1. Right? So that's what U of n minus L of n is. And so how can we show that that is bigger than 1? Well, let's go ahead and square both sides. And notice that that is equivalent to 5n squared minus 2n plus 1 is bigger than 1. Great. But now notice that that is equivalent to 5n squared minus 2n is bigger than 0. We can move 1 over. Great. But now we can pull an n out of that. And notice that that is the same thing as 5n minus 2 is bigger than 0. Okay, good. But now notice, since n is a natural number, we know that this part is always positive and this part is also always positive. So that means this checks out. There is always a natural number between u of n and L of n. So we've checked these two things carefully. Now we are ready to move on to the next step. Okay, so on the last board, we checked some really subtle details to make sure that everything is in order and everything's okay, and it was. So now, the next thing we want to do is use this fact right here. M of n is the largest m such that this is true, which means we don't really need this lower bound anymore. What we need is the following. So we need to notice that m of n will definitely be bigger than u of n, smaller than u of n. And then also notice it has to be bigger than u of n minus 1. Great. So, and just as a heads up, notice that we know for a fact that L of n is to the left of u of n minus 1 by something we showed on the last board. Okay, so let's argue why m of n needs to be bigger than u of n minus 1 and u of n. Well, we know that there is a natural number between these two. And we also know that there's at most one natural number in between these two. So what that will tell us, since m of n is the largest such, well, it has to be bound between these two. Okay, great. But now we can apply the squeeze theorem to show that the limit as n goes to infinity of u of n minus 1 over n is less than the limit of m of n over n as n goes to infinity, which is less than or equal to the limit as n goes to infinity of u of n over n. Great. But now notice that this thing right here is just equal to the limit as n goes to infinity of u of n over n minus 1 over n. Great. But this part clearly goes to 0. But we're only really allowed to do this if the limit of u of n over n exists, but we will show that it exists. So notice that the limit of m of n over n is bound between the limit of u of n over n and this thing that goes to 0, so we can disregard it, and the same thing, but in other words, the limit as n goes to infinity of m of n over n has to be the same thing as the limit as n goes to infinity of u of n over n. Okay, good. But we have a nice formula for u of n that a Calculus 1 student could use in order to calculate this limit, and so that's what we'll do. I'll clean up the board and then we'll finish it off. Okay, so on the last board we argued that m of n had to lie between u of n minus 1 and u of n, where u of n was this. Okay, great. And then it follows, using the squeeze theorem, that the limit as n goes to infinity of m of n over n, which is our final goal, has to be the same thing as the limit as n goes to infinity of u of n over n. And so let's go ahead and calculate that. So notice this is going to be, I'm going to bring a half out, so this is going to be 1/2 the limit as n goes to infinity of 3n minus 1 plus the square root of 5n squared minus 2n plus 1 all over n. Okay, good. But now what I'm going to do is I'm going to break this into pieces. So this is going to give me 1/2 the limit as n goes to infinity of 3 minus 1 over n. So I have 3n over n minus 1 over n. Plus, now what I can do is I can bring this in under the square root if I square it. And so let's just recall what I'm doing here. I'm saying 1 over n is the same thing as the square root of 1 over n squared, which is true if you have a natural number. There's something to do with absolute values if you have maybe a negative number, but we're okay here. So that means we can write this as 5n squared over n squared, which is 5, And then we have minus 2n over n squared, which is going to be minus 2 over n. And then finally plus 1 over n squared. Great, so that's how all of that simplifies. But now notice this term is going to go off to 0, and then these two terms are also going to go off to 0, which gives us our final answer of 1/2 times the quantity 3 plus the square root of 5. Great, and just to reiterate, that is the limit of this function m of n over n, where m of n gives us this largest m such that this inequality is satisfied. So that finishes this problem.